When undertaking projects requiring verification of grounding electrode system resistance, such as achieving 2 ohms or less to earth, renting a ground resistance tester like the Fluke 1625 can be a cost-effective solution. It's important to locate reliable rental companies that offer the specific equipment needed. Several rental companies specialize in test equipment, including the Fluke 1625. Firstly, TTI Test Equipment is a company to consider. Secondly, Rent-Equip offers rental options for grounding resistance testers, including the Fluke 1625. Thirdly, Granger also provides the Fluke 1625. In addition to these, consider US Instrument Rentals, Test Equipment Rentals, Aminus One Calibration and Metrology, and Danaher Rentals as alternative sources. When contacting rental companies, directly inquire about the equipment's availability and pricing, as these can vary. Specify the exact model number, in this case the Fluke 1625, and the duration you need the equipment for. It is important to ask about any additional costs associated with the rental, such as shipping fees and insurance coverage. Also, consider potential shipping delays and ensure you allow sufficient time for the equipment to arrive before you need to use it. Carefully read the rental agreement before signing it to fully understand the terms and conditions. Ground resistance testers like the Fluke 1625 operate on the principle of measuring the resistance of the earth grounding system. This is crucial for ensuring electrical safety and the proper functioning of electrical equipment. The Fluke 1625, in particular, is a popular choice because of its accuracy and ease of use. Ground resistance is measured using techniques like the fall of potential method, which involves injecting a current into the earth through an auxiliary ground electrode and measuring the voltage drop between another auxiliary electrode and the grounding electrode under test. The measured voltage and current are then used to calculate the resistance. A low ground resistance is essential because it provides a low impedance path for fault currents to flow back to the source, allowing protective devices like circuit breakers to trip quickly and clear the fault. This helps to prevent electrical shock hazards and equipment damage. The requirement for a grounding electrode system to have a resistance of 2 ohms or less is a common standard specified in many electrical codes and regulations, such as the National Electrical Code, or NEC. Adhering to this standard ensures that the grounding system is effective in providing a safe path for fault currents. The presence of an engineer during the testing process ensures that the testing is conducted correctly and that the results are accurately interpreted. Engineers can also provide guidance on interpreting the test results and recommending corrective actions if the grounding system does not meet the required specifications. When using a ground resistance tester, it is important to follow the manufacturer's instructions carefully. This includes properly connecting the test leads, selecting the appropriate test range, and interpreting the test results correctly. It is also important to ensure that the soil conditions are appropriate for testing. Dry or frozen soil can significantly affect the accuracy of the test results. In such cases, it may be necessary to wet the soil around the auxiliary electrodes to improve the contact resistance. Grounding is a critical aspect of electrical safety, and ensuring that the grounding system meets the required specifications is essential for protecting people and equipment from electrical hazards. Renting a ground resistance tester like the Fluke 1625 can be a cost-effective way to verify the effectiveness of a grounding system, especially for short-term projects. When dealing with electrical grounding, always consult with qualified professionals to ensure compliance with all applicable codes and regulations. The Fluke 1625-2 specifically is an advanced earth ground tester which can measure ground resistance using several methods. The 3-pole fall of potential method is used for basic measurements. The 4-pole fall of potential method allows for more accurate measurements, especially in situations with high soil resistance. Selective testing, using a clamp-on transformer, enables measurement of individual ground rod resistance without disconnecting them. Stakeless testing measures ground loop resistance using 2 clamps without needing ground stakes. Measurement ranges typically span from 0.25 ohms to 1999 ohms, covering a wide range of grounding system requirements. It also measures alternating current, or AC, and direct current, or DC, voltage from 0 volts to 50 volts. Data logging capabilities are often included to record measurements for reporting and analysis. The tester often has a rugged design to withstand field use, and safety ratings meet stringent standards. Proper use requires understanding the test setup for each method, correct placement of stakes or clamps, and interpretation of readings according to standards. Soil conditions, as mentioned earlier, can affect measurements, and moistening the soil may be needed. Always disconnect equipment before testing to avoid inaccurate readings and potential hazards. Regular calibration ensures accuracy. Always consult the manufacturer's manual for detailed instructions and safety precautions. Ground testing ensures safety, compliance, and proper operation of electrical systems. It verifies that the grounding system can safely dissipate fault currents, protecting personnel and equipment from electrical shock and damage. A low ground resistance ensures a quick path for fault currents, allowing protective devices to operate promptly. Compliance with electrical codes such as the NEC mandates regular ground testing. Improved equipment reliability is achieved because effective grounding prevents voltage fluctuations and reduces the risk of damage. Proper testing identifies corrosion or loose connections in the grounding system, allowing for timely repairs. Testing is crucial during installation, maintenance, and after any modifications to the electrical system. The three-point fall of potential method involves driving 2 ground stakes into the soil in a line away from the ground electrode under test. The distance between the stakes should be significant, typically 20 feet to 50 feet, to avoid overlapping fields of influence. The tester sends a current between the ground electrode and the far stake, while measuring the voltage drop between the ground electrode and the near stake. Resistance is calculated using Ohm's law. The 4-point method is similar, but uses an additional stake to improve accuracy, especially in areas with high soil resistivity or where stake placement is limited. Selective testing involves using a clamp on current transformer to measure the current flowing through individual ground rods in a multi-grounded system. This allows for the assessment of each ground rod's effectiveness without disconnecting it. Stakeless testing uses 2 current clamps placed around the conductor under test to measure ground loop resistance, eliminating the need for ground stakes. This method is useful in paved areas or where driving stakes is not feasible. Soil resistivity affects ground resistance measurements. High resistivity soils require longer ground rods or soil treatment to achieve the desired resistance. Moisture content, temperature, and mineral content all influence resistivity. Soil testing can determine the appropriate grounding design. Grounding system components include ground rods, grounding conductors, and bonding jumpers. Ground rods are typically copper or copper-clad steel, driven vertically into the ground. Grounding conductors connect the equipment and grounding electrodes, providing a path for fault currents. Bonding jumpers connect metallic parts to create a continuous ground path. Proper installation and maintenance are essential for effective grounding. Connections must be tight and corrosion resistant. Regular inspection should check for damage or corrosion. Grounding systems should be tested periodically to ensure they meet required resistance levels. Understanding and implementing effective grounding practices is crucial for electrical safety and reliability.